Okay, so we've got, I want to do a few lectures today. I want to do a lecture on PD control, a lecture on PID control, and a lecture on lag lead control. So hopefully we're going to get through all of those. And not only that, we're going to talk about the project today. So
your normal lecture is an hour long. You always ran over.
So we have 4 hours, right? No. We're gonna see. They're gonna actually. PD might be the longest one, actually, kind of counterintuitively, but the idea is a little bit new, and then we reuse that idea and the integral idea in the PID one, and then we kind of do the same exact thing in the lag lead controller. So it's really, it's not. We're going to see a lot of the same things happen over and over again. So might be able to move quickly. That's my hope. So let's shoot. I would like to do this, like 40 minutes, 40 minutes, 40 minutes, and then, see. So we'll give it a shot. So we'll jump in. In this section, we learn controller design with the following aspects. Ideal control. So that's, ideal derivative control. Wow. The first sentence. Issues. Oops. Ideal derivative control. Which is a pure derivative. 2, an active control aspect. So this controller can only be implemented with an active circuit, so you can't build this out of capacitors and inductors. We're using cascade compensation, which is the forward path compensator, like we have been already, and transient response compensation. So finally, we're going to design for transient response. So far, we only learned how to design, we learned how to design for transient response by adjusting the gain, K. That's the only way we've learned how. But our goal with integral control was to avoid moving the root locus around, right? We wanted to leave it kind of alone and just get the integrator in there. And so that was the integral compensation and the lag compensation. They left sort of the root locus alone. Now we're going to want to move that root locus to go through a specific desired dominant pole location. That's what we want. So we can just dial it in where we want to be. And so that's our goal with derivative control, compensation. When designing for improving transient response, we will usually want a specific overshoot and a relatively short settling time. So we'll say, we want a specific percent overshoot, like 10% overshoot or less, maybe. A settling time of maybe an improvement by a factor of something over proportional, or maybe it'll be a specific time. Like I want settling time less than 1 second or something. So that's actually something that we have to worry about with our project, right? We care about settling time. So that's something we might think about that when we're doing our analysis of our system. So adding, and by that I mean literally summing a differentiator S to the forward path gain called PD control or ideal derivative compensation will typically speed up the response. It's not universally true, but typically if you put in a differentiator, it's going to speed up the response. The idea is that, so if you put in a differentiator S, that means that you're adding a term to your control effort. It's really annoying. I have these turned off. I don't know why. I don't know. Anyways, I gotta figure that out. So you guys might see something embarrassing from like Victoria's Secret or something. That would suck. If it actually happens, it'll just be funny now.
You
Thank you. Thank you. I appreciate that. I appreciate your openness and willingness to accept. It's very Benedictine of you. Yeah. Okay, so our proportional, so remember, let's think back to what our proportional control does. It actuates the system in proportion to the amount of error we have, okay? So it's sort of like a spring that has a force in proportion to the displacement. The proportional controller has an actuation amount in proportion to the error, okay? If we add literally sum a differentiator, we're going to be adding a term that is proportional to the derivative of the error. And back, and I think I may have forgotten to mention this, when we have the integral error, the 1 over s, the integrator, I think I mentioned it in passing, but I probably didn't stress it enough. We're actually integrating that error function. Okay, so we're adding a term that integrates with the PI control. We're adding a term that differentiates with the PD control. So it kind of makes sense that if you're differentiating and your error starts to increase suddenly, you're going to get a strong response from your controller if you have some derivative control in there. So that it kind of makes sense that our system's going to respond quicker to things with some derivative control in there. But it's something that you have to be very cautious with, because you can, if you have a noisy signal, so say your error signal looked like this. What is the derivative of that? What does that look like? Wildly swinging, extremely high values, right? So, and it's gonna go from positive to negative, positive, negative, positive, negative, and so your controller will freak out. That's what essentially what happens. So, if you have a noisy error signal, you have to be really careful with using derivative control. You should be cautious in any case. And yeah, so when we add this differentiator in there, we get to place it where we want. We're not going to sort of cancel out its transient effects by putting a pole in there. The reason we're not doing that is we actually want to move our root locus around this time. Remember, the reason that we put in a 0 when we had our PI control or our lag control, the reason we put in a 0 was to cancel out the effects of putting the pole on there. Now we're not going to put a pole on there to cancel out the effects of the 0, because we actually want to move that root locus around, and we're going to want to move it around to a specific location. Okay. Now you technically could move around the root locus with a pole, right? So when you do integral control, you could say, okay, we're just going to put in an integrator term, but we're not going to put in a 0 to cancel out that effect. And it'll affect the transient response. Maybe for the better. I mean, it's possible. It might not be, it might not be bad. It could be good. But most likely you don't want to do that. When you're thinking integral control, you're thinking, I want to improve my steady state error. When you're doing derivative control, you're thinking, I want to improve my transient response. So that's what we're going to focus on here. So we want to affect the transient response. And that's why we put in a 0. And so our goal, as we design this, is going to be, where do we put that 0? So where do we put that 0, that differentiator 0? Are we going to put it just randomly somewhere? If we put it randomly somewhere, it's going to affect that root locus randomly, but we want that root locus to be affected in a very specific way, to go through a specific location so that we can see the transient response that we want. So let's talk about the design procedure. This is one that the design procedure, I write it down, but I have to admit it's really hard on the first pass to understand all the steps. So I'm going to immediately on the next page do an example of this. And I think that's where most of the understanding will come, but we'll still go through the design rules as sort of a first pass on this. And then we're going to have to go through it in detail in the example. So step 1, design a proportional controller to meet as closely as possible the transient response specs by choosing the gain, K, for the dominant closed loop poles to be SK. So we choose a gain, just like we did design a proportional controller for all of the previous problems. We try to get as close as possible to the transient response that we like, but if we're going to need to do PD control, it's not going to be the transient response we really want. It's going to be something that falls short of what we want. So typically we can meet the overshoot requirement, but often not the settling time. Does anybody know why that is? Why can we often meet the overshoot requirement, but not the settling time requirement?
Does the PI not deal as much with the transient response?
So not so much that, no.
Doesn't
Because,
no.
I was going to say, because you're on that ray of constant damping, and if you're on that ray that rays your natural frequency, the length of that ray is, right? And so
Yeah.
You're selecting it. If you're always selecting that along that ray,
You'll get the right damping. So you'll get the right. So the overshoot is directly related to damping. So there are those rays of constant damping, right? That go out from the origin, and those rays of constant damping, oftentimes the root locus will cross them. Okay, not for every system, but oftentimes you'll be able to pick whatever your percent overshoot is. There will be a ray that comes out, and oftentimes it'll intersect. Maybe not, but in many cases it does. So you can actually get on that ray and get your percent overshoot with proportional. But if you want to speed that up, if you want your settling time to be less, then you actually have to move your pole to the left, right? And so you don't want to be just anywhere on that ray. You want to be out on that ray to the left more. And your root locus, unless you're just extremely lucky, is not going to go through that point. It's probably going to be somewhere else on the ray. So that's one way to think about it. Sometimes it's the other way around. You can get the settling time, but you can't get the overshoot. So it just depends. So step 2, determine the closed loop dominant pole locations, SPD, from the transient response specs. So these are the desired closed loop dominant poles. This is assuming, so notice all of our transient response tools have to assume a second order or first order, but most likely it's going to be second order dominant system. That the dominant poles are going to be second order poles, second order conjugate pair. And so when we say like that the damping ratio is related to the percent overshoot, that's assuming it's a second order system. Same with settling time as well. It's equal to the settling time is related to zeta times omega n, the natural frequency. So that's also assuming it's second order. But in fact, most of our systems are not second order. And what do? We still assume it's second order for the design equations to get us there. And they will likely be a little bit off because it's not perfectly second order. But if it's close enough to second order, it'll get us in the ballpark, and then we can tweak things to meet our requirements. So the actual percent overshoot might not be what we design it to be. So like we might design it to have 15% overshoot, but it might end up having, 23% overshoot. Well, that's not great, but at least you're in the ballpark, and then you can tweak from there. So it always depends on how good of an approximation your second order approximation is. So I recommend two things. Assuming it, pretty much your design tools require you to assume it in these cases. But then, you can check using the equations in the end. Like you can check using, is the pole, are the two poles at least, I guess, 1/5 of the wave to the next pole. That's not really, that's like a sort of a guideline, but that gives you a pretty good idea if it's going to be correct. But the best way to do it is just simulate it and just see, like, what is my percent overshoot? You can compute that from a simulation really easily, so that'll give you a pretty good idea of how good your second order approximation was too. And that's the definitive answer, right? It doesn't matter how good your second order approximation is. What matters is how well you meet the spec. You can come up with it could be like a most ridiculous assumption that this is second order. It's so not second order, and it's totally not dominated by these poles. But your design got you close enough, and then you could tweak it to get within the percent overshoot, and you still met the specs. So that doesn't really matter that you used a tool that wasn't totally valid along the way, because you threw that away anyways. It doesn't matter. Okay. So we decide where we want those closed loop poles to be. We'll call them SPD. So I'll just take, say, the positive one. So say it's a conjugate pair, like you want a certain settling time, it's underdamped or whatever. And you set them out there. These are where you want your poles to be, based on the settling time and the damping ratio or the percent overshoot. And typically we choose the SPD to be alpha SK. So assuming that we got on the damping line we want to, on the damping ray we want to, we can simply scale that value to keep it on that damping line. Because if you scale a complex number that's already on a ray from the origin outwards, it's going to stay on that ray. It's just like if you're scaling a vector, it's just going to make it longer, right? But it's going to have the same direction. So you just can scale it, and it's going to decrease your settling time. And alpha is actually the factor by which we reduce the settling time. So you scale it by the factor you want to reduce the settling time. Now, that's, once again, based on the second order approximation. So we'll scale it by that, and we might need to go back and tweak it. But that's a good start, is scaling it by that, and that'll be our desired closed loop pole location. Okay? Step 3, compute the required compensator angle contribution to be from the angle criterion, pi minus whatever the angle is of the transfer function, open loop transfer function, when you plug in the desired closed loop or the desired closed loop pole location. So remember back when we developed the root locus, we developed two criteria for being on the root locus. And the two criteria were the magnitude criterion and the phase criterion. Remember that? Vaguely. The magnitude, and what they were was, it said that if you evaluated a transfer function at some point, and if it's on the root locus, the magnitude of the transfer function at that point had to be equal to 1, and the phase had to be equal to 180 degrees, or pi, plus or minus 2 pi. So you can keep going around, right? So that was the requirement based on so the magnitude criterion was that the magnitude has to equal 1, and the phase one is that the phase has to equal 180. And from that, we talked about how you can think about evaluating a complex function at a given point as being the as summing up all of the angles to meet the angle criterion. So if you drew, I'll just do a little sketch here. If you draw, say you had root locus that looked like this. So say you had pole, and you had locus in between, and then they go off up and down. Say that was your system. Then the angle criterion says that if you were to pick a point anywhere on this, say we'll pick one on the real axis here, if it's on the root locus, then the angle of the poles, so that means this angle, the angle from this pole to this point. So if you drew a vector from x to this dot, the angle of it's 180, right? And the angle of this point, if you drew a line directly to that point, is 0. You add those up, and if they're equal to 180, which in this case they are, you're on the root locus. If you're over here and you did the same thing, the two angles would be 0, right? And they would not add up to 180, so you would know there's not locus here. The same holds for a point up here, too. So if you drew the line, that angle is going to be, I don't know what it is, 110, 120, something like that. And this angle here is going to be, 80 or 70 or whatever it needs to add up to 180. So that's true. But if we add a 0 in there, the whole thing changes, right? The whole thing changes, which is actually good because we want to move this root locus around. But we want it to go through our test point, wherever we desire it to be. And in order to do that, we know that at that point, the 0 has to be placed in such a way that it contributes the right amount of angle, right? And that's the way that we fix where that's going to be, is we decide how much angle we need to contribute, and then we back out where that 0 should be located to contribute that amount of angle. And that's like the whole trick. I mean, we got to do quite a few little calculations, but really all we're doing is we're contributing a new 0, and we have to contribute it so that it moves our root locus in the right position. So that's what we do in step 3. We decide how much that angle is that we need to contribute. In step 4, we include the compensator in the forward path, and we choose ZC such that it contributes that angle. And this is the formula that gives you that relationship. And that's just essentially trigonometry that gives you that angle. So it's pretty easy to compute. I will try to go through the argument a little bit in this problem so that you can kind of see how to do it, but it's just trigonometry, but trigonometry is non-trivial if you wade into it too, so it is a little messy, but it's not too bad. Okay, 5, tune the gain. So now we have a root locus that goes through the point we desired, right? We were able to just dial it right in and go through there. Now we need to choose the gain so that those closed loop poles are at that point. So our old gain isn't going to necessarily get us to the point on the new root locus. So we need to retune for the new root locus and get to that point. So now we're good to go. We're at that point. Check the second order approximation. You could do it by seeing if you're, how far out your next pole is and all that. Or you can just do step 6, which is to simulate and see if it meets the specs. It's another way to check. So that's our last step. So it's quite similar to the PI control, except that there's a little bit more involved in deciding where that 0 is going to go. Okay? All right. So we're going to use the same plant to design a PD controller with 15% overshoot and a settling time 3 times faster than you can get with proportional control alone for the unity feedback shown. So, and I think that there was I don't think I included the requirement that we get, 15% overshoot. Yeah, so I said 15% overshoot. 15% overshoot, and we want to do, so with proportional control we can get 15% overshoot, but we want to get 15% overshoot in a third of the time, right? So that's nice. I mean, it's nice to be able to say, okay, I want that overshoot, but I also want it to happen faster. So that's cool. Okay. So part 1 is exactly the same as before. We design our controller for 15% overshoot, which I don't know if you guys can see that very well, but it says the gain is 68.9, and the pole is located at negative 1.56 plus or minus J 2.58. Looks like this one was at 4.8. I'm not sure if I transcribed that incorrectly or chose a slightly different point, but in any case, it's close. So that's close to 15% overshoot. I chose to be a little bit on the low side of overshoot. This is kind of me being cautious about what's going to happen next, because remember that this is, this second order approximation. We might not be perfect, so we got to be, because we have a third order system. So I'm being a little bit cautious with my spec here to begin with. Probably, don't need to be on the first round, but I chose to be. So I chose to be at, 13.5% overshoot. Not bad. Okay. Now, to compute the desired closed loop poles, what can we do? I mean, for this problem, how are those desired closed loop poles related to the closed loop poles that we get with just a proportional controller? How is it related? Because so our proportional controller is on the right ray, right? And we got to the right ray, but what does that mean? Is that good? Are we happy with that? We want to get 3 times faster, right? Than that. So what do we do?
Scale that vector from origin to that point.
Yeah, which is essentially just scaling this complex number by 3, right? So let me get. Soon I will need my notes. Oh. Crazy. I printed off the wrong one. Ah, well. We'll do it on the fly. We'll do it on the fly. So, our desired closed loop poles are going to be at like out here, so it's like triple the distance. So that was our original one. We want to go out here. And I think I know what I was showing. I was showing up here, I was showing this one's close to 15% overshoot, but then I did a new root locus that was a little bit more finely spaced in omega, or in K. So that is a little bit confusing to see two of the same graph. So this is online, this MATLAB script. So if I put in the open loop system, I do a root locus of the system. Remember how before, if we do this, I have to close MATLAB. Hold on. I found out a fix for this. I just have to close MATLAB and reopen MATLAB. And then
the exact same problem in the video. I'm pretty sure at the exact same spot where you said, "Oh, MATLAB won't open."
yes,
Restart it.
I have to restart MATLAB because what it does is it can't figure out how big the screen is, and so it makes the figures. It thinks it's in a window that's a different size, and it makes the figures the wrong size, so you can't see like 3/4 of it. It's ridiculous. I have no idea why it does that, but I'm glad that I figured out this workaround. I was making them into subplots artificially to squeeze it in, but that's really annoying. So let's see. I think that this fix works. Yeah, it works. Okay, I just have to restart MATLAB. The universal fix for everything. So I want to have 15% overshoot. We could compute what the zeta line is we need to be at, but it's kind of convenient that MATLAB has percent overshoot pop up here for us. So this is it. So I can't get to 15. I can get to 13.5 and I can get to 17.7 with the native resolution that they give me on ArtLocus. But I can't get 15 exactly, can't get any closer than that. So my gain's between 64 and 77 probably. So that's why I do another one between 63 and 77 in increments of 0.1 in gain. So that's why I do that finer mesh. So I'm sort of showing you guys this. I mean, I didn't have to do both of them, but I want to show you guys how you would go through this process. And you would say, oh, okay, I need a little bit more resolution. So now I zoom in and I say, okay, I need 15%. Okay, so it's any of those three is a valid choice. So gain of like 68.9. That's what I chose. Boom. Okay. So now my desired closed loop pole is out here, right? So we're right here with the gain. Desired closed loop pole is out here. So step 2 is to compute it. And like we just heard, we could compute S. I called it PD in my design rules. SPD, we want it to be 3 times faster, so we have to scale SK, or I call it SP in the design rules, SK by 3. Okay? So we need it to be equal to, in MATLAB, I just define S1 to be this, and then I just say whatever the factor we want to improve, we'll call N. I'll scale this design point by N to get S2, or SPD I'm calling it here. If I evaluate this, then I get S2 is negative 4.68 plus 7.74 j. So j 7.74. Good. So we know where we want to be, and we're out here. Now, here's like the most difficult part of the problem, in my opinion. That is computing what this angle is. So the zero's angle contribution to move the root locus through SPD is, and this formula that I'm giving you, I didn't have time to verify. I can't recall if this formula has to be changed by 180 degrees depending on the quadrant you're in. I need to go back and check that. The book doesn't give a general formula for it. The book always just does this ad hoc geometry, trigonometry problem. And although you do get some insight into that, it is nice to know the general formula. I can't remember if this is one that you have to adjust in a different quadrant or not. It should jive with your physical understanding of what the angle should be. Okay, so keep that in mind. This is the zero's angle contribution to move the root locus through SPD is, so we're going to call it theta c equals pi minus it's I said g of, it's the angle of g of SPD. So we could do angle of g of SPD. It's not the angle of SPD. You need to actually evaluate it in the transfer function, because that's how much it contributes to that angle. So that is not something that I would want to do by hand, typically. It's an angle that's pretty easy to compute, though, if you use MATLAB to compute it. To use MATLAB to compute it, there's a really nice function called eval_fr. That stands for evaluate frequency response. It also works for evaluating a transfer function at a certain value of s. So it's a really nice little function.
What's the word again?
It's eval_fr. Eval_fr. And in MATLAB, I wrote down theta uncompensated. So this is the, we're going to set it equal to that. We'll compensate for this angle. So this was sort of a semantic thing where I said theta uncompensated is this, and we want to compensate for that angle. So that was a little, I actually regret using that double notation there. But essentially, you need to compensate by pi minus the angle of g of S2, or the design point that you want to be at. Okay? And that gives us theta c, so I already evaluated this. So theta c is 1.626. 626, which, if we do that in theta c times 180 over pi, so in degrees, we get 93.2. So we need to compensate for 93.2 degrees that we're not compensating for with this zero. And that's our desire. So we need to choose so we need to choose ZC. Okay. Now let's go ahead and put do a little geometry or a little trigonometry here. So we'll put our desired pole location, the positive one, out there. We're just going to deal with the positive one. So we want it to be there. And we have to put a 0 somewhere So that contributes this 93.2 degrees. So by my reckoning, you'd have to be not quite below it, but a little bit to the right of it. So you'd want to have the angle here be theta c, okay? And we need to compute what that, we know where the pole is. That's our desired pole location, right? But we don't know where this 0 needs to be. We just know the angle this needs to be at. But it does fix it. We just have to do the trig to figure out where that is. And so I would draw a triangle here to the origin. You know this angle. You need to know this side. So you can do the trig however you want. I chose to do it the way that gave me this formula for it. So using the imaginary and real parts of the design point and the tangent of theta c, which are all known things. So we can say that ZC is equal to negative imaginary, the imaginary part of the design point, SPD, plus, is it divided by, divided by tangent theta c, divided by tangent theta c. So that whole thing plus the real part of SPD. So the real part makes up, so notice, I mean, the way that I'm thinking about this is notice that the real part is of SPD is like this whole length. I can't see that very well. Is like this whole length. So we need that whole length minus whatever this part is, right? That's the part we need to subtract out. And so that's what this term is. So that's, I don't know. Everybody likes to do their trig differently, so I'm not gonna hold you guys to do it in a certain way. I actually don't even encourage you to do the trig every time. I encourage you to do it once so you get the feel for it, and then just use a formula because it's better. Yeah.
The Pythagorean theorem wouldn't work on complex plane, right?
Pythagorean theorem would work on a right triangle. So you could find that whole thing, but you can't find it. So you'd have to use.
Yeah, I know. I'm an idiot.
So, but we do know. I mean, we already know that distance. We already know that distance out to the pole location. Okay, so now we know where ZC is. So let's compute it. And I'm having MATLAB do that part because I don't want to, but this is just that formula. And so let's see, what did ZC come out to be? Negative 4.25. All right. Easy enough. So now let's see. So we have our compensator designed now, right? But we don't have the last gain adjustment. So we now have a root locus that goes through the design point. So we know it's possible to get there, but we don't know what gain it needs to be. So now we have to go to MATLAB and do a new root locus. And first off, this is the main root locus. That looks quite a bit different than it did before, right? Notice how it pulled that 0. So notice here are the original open loop poles, those 3. That 0 is pulling the root locus that way. And we actually, it's really useful to think of zeros as pulling the root locus around, and the poles as pushing them. And actually, some people think of them as being like magnetic, or no, actually they think of them as being electronic poles that are attracting and repelling. I don't have a great intuition for that myself, so I don't really find a lot of value in that. But it is useful to at least see that. So if you put a 0 somewhere, it's going to sort of pull it in. Okay, now we're saying that our design point should be on here. I mean, we did some rounding and stuff like that, so it might not be perfect, but our design point should be essentially here. So we should be able to adjust our gain, and I'm going to tell you that I do the same thing where I tried it, and I said, oh, it's got to be between these 2 points. So let's look a little bit more specifically along this region here, and we want an overshoot of 15, right? So somewhere in there, 82.4, 82.5 for our gain. We get our overshoot. We're just basing our settling time off of the idea, the design formula idea, that if we move it triple to the left, it's going to reduce the design time by that factor. So, or the settling time by that factor. So that's based on the second order approximation. We don't know how well that's going to actually work out, but we do know that we did move it triple to the left. So we did succeed at that. So let's try. So our pull ends up being at negative 4.68 plus 7.76 approximately. So that gives us, we get a gain of K equals 81.3 is what I chose. And the pull ends up being what are we calling this? Well, I'm calling it here. Did I actually even define it? I did, I think. I didn't really define it. But if you wrote down what this point is, I mean, it's close to our design point. It might not be exactly on it because we did do some rounding and some roughing. So then all that's left to do then is use this gain and see if we meet our specs. I mean, in theory, we have a percent overshoot of 14.8. I mean, if it's really second order, then that's what it would have. But it's not second order, so we don't know how good it's going to be. Let's try to simulate it. So we choose this gain, 82.3, and we simulate both systems. We simulate the proportional one, which we can use the feedback command in system 1 times K1, feedback command system 2 times K2. System 2 has the 0 stuck in there. Okay, so system 2 we decided is going to be the original system multiplied by a 0. So we put the differentiator in there. And yeah, we'll go ahead and do this the simulation then. So we'll simulate from 0 to 5 seconds. We'll do a step response of each, and we'll plot them. And I'll do this one first. So let's see what it looks like. Okay, so proportional controllers in blue. Just eyeballing it, looks like we did approximately what we set out to do. We have to figure out exactly what our overshoot is, and we have to figure out what our settling time is. So instead of actually doing that all manually, I recommend using this really nice thing called step plot. Okay? It's a nice command called step plot. And step plot allows you to look at let's see, that's well, okay, so that's not, so that wasn't step plot, my bad. So step plot shows you the step response as well. I don't know why I decided to add that on there, but step info is what you want to use. I showed it to you the other day in passing. So it gives you what the rise time is, the settling time. You can use step plot to show you those, and that's what I used to create these two plots. I think you can use step plot, and you have to I think you have to pass an argument to it to make it print out all those things. I don't remember having to pass an argument. It could have changed. I have a newer version of MATLAB than I had before. So, anyways, somehow you can get them to print out on there, or you can just use step info to have it print out. So we have the system 2. We have a settling. I think we use settling. See. I can't see it for some reason, but yeah, I don't know why this stuff isn't showing up, but anyways, so our settling time is, so we've achieved our settling time and damping specs, I claim. So our percent overshoot is 18.9%, which is higher than the spec though, right? That our spec was 15%. So we want to do better. We can adjust, and we'll do that in MATLAB. I'm not going to do that in the notes. And then improvement in the steady state error is a pleasant surprise, but we need to be careful because know that it does not happen in general. Okay, so I didn't show this, but in MATLAB, our comparison plot here, our PD controller is better in steady state response, right? It's not 1, which it should be 1, but it's better than the P controller is. So we've got that going for us. But that's generally not going to happen, or I mean, it can happen, but it's an accident. So don't expect it to happen. If it happens, it's great, but if it doesn't happen, don't be surprised. Okay. If we wanted to do better than this, we could explore with things. So we should probably go back to our first step and maybe go for a little bit more conservative of a percent overshoot and try again and see. We could start adjusting the gain here, right? So we could adjust the gain so we meet our percent overshoot spec. But I think from the root locus, which I showed here, from the root locus, it's actually not bad. So we could probably just tweak the gain and get to a percent overshoot that we want. So we could probably drop the gain a little bit and get inside our percent overshoot spec. That's my guess. We probably could do that. We could try, and then we would be able to. We would sacrifice a little bit of settling time because it's going to move a little bit to the right. See how this is sort of sloping that way? So we could go back though and start with the previous step, know where it's going now, and be a little bit more conservative with our estimate. And then maybe we should try our test point. We could maybe multiply it by 3.5 or something like that. And then even if we have to give up a little bit, we can give up a little bit. It's not a big deal. So we could be more conservative in our previous steps to get to the final answer, and we would probably get the right, or we'd probably meet our spec. That's one way to go. I wanted to introduce this idea, though, and this is the last thing before we break for the next lecture. There's this really cool tool called the SeeSo Tool in MATLAB, and I don't spend a lot of time on it because I don't want you guys to feel like this is the way to go. I think this is really cool for getting a feel for how these root locus plots change for the pole location, zero location. So that's why I'm introducing it to you now. I'm not giving it to you because I think it's a great way to design. I think it's okay. It's not terrible, but it's just not my preferred method. So I will show it to you nevertheless because I think it's kind of cool. So what you can do in this is you can like add the graphical tunings. You could add a zero or a pole in here, and you can look at the response plot. So I'm going to look at a step response of the input to the output. Okay. And the first thing you can do, this is just our regular open loop. We haven't put in a compensator yet, uncompensated root locus. You can increase the gain by moving these dots around. I think I'm going to have to manually, there we go. So you can increase the gain by just moving the dots around and seeing what the step response, how the step response responds to that. So we would expect as we go up here that our settling time is probably going to get longer, right? And we're going to oscillate more and more, right? So if I continue to drag it up, we're getting greater and greater overshoot, right? And our settling time keeps rescaling, but now we're at like 15 seconds to settle. Whereas down here, in just a few seconds it settles. Okay, so that's like one way. So you can get a feel for the gain adjustment. That's kind of cool.
Will it show it diverge when you move to the right of the axis?
I don't know. Let's see it probably. Yeah. Yeah, you probably can't get it right on zero. Right on the imaginary axis. That's close. That takes 1,200 seconds to ring down all the vibrate. That's interesting. So, okay. But so instead of just doing the gain, though, we can add a compensator on here, which is cool. So look what we just did. We added a zero. We took a zero and we placed it where we wanted it to be to make our root locus go through a design point. So let's take a zero and we can just click anywhere we want. Let's put a zero way out here. Boom. So that's what happens if we would have totally miscalculated. Well, let's move the zero around and watch these things respond. So look at how the root locus is moving around. So if you make the zero way out here, it goes unstable without too much increase in gain. And if we move it in further and further, it becomes stable for more gain. And then we switch sides. Notice how it feels like the zero is attracting the root locus to it. So as I move it around, that zero is being attracted to it. And I can move it way over here. Really fascinating stuff, isn't it? But where do we stick it? We stuck our at negative 4 point something. 4.25. So negative 4.25. Pretty close. And then we adjust the gain around. So what did we choose for our gain? 80 something?
82.3.
Oh yeah.
So if you had chosen to move the zero further to the right, it would have changed locusts are
Yeah.
more, but would that have been able to fix, because that would change your angles. We solved this by solving first for the angles and then going that way. It
Yeah.
would have been better to have done it the other way, to have changed the root locus so it was almost a straight up and down line on the value we wanted.
Well, see what happens is we move, it's gonna pass through our point as we move it to the right. At some point, we're gonna pass through. So our point is like, let me see if I can show you. Well, I can't really show you. I'll put where my hand is. So the point's probably like right here somewhere. Okay, where the grab hand is. And as I keep moving the 0 to the right, we pass through that point, and then we continue through it. So we really do have to compute the angle we want to put it there. Now, you could move the pole further to the right to shift everything in the root locus to the left a little bit, and your settling time is going to be even better, right? So we could go back and say, okay, well, we want to do even better on settling time, so we do that, and then we adjust our gain appropriately. So the one thing I'm going to mention, though, the little gain that it says here, loop gain, as I recall, this gain is not the same gain that we're calling our gain. They're using a different scaling, and the scaling that you can see, or you can see the scaling if you go into the compensator editor. You can see, like, it says that the gain is 531.67. The reason that is that they factor out from this compensator 0 here. So their scaling is different. They make this a 1 instead of S a 1 as we're doing. The coefficient of S for us is 1, and then this coefficient is 4.25. And that makes this value a factor of 4 different. So their gains are a factor of 4 point whatever different. So their gains are different than our gains. So we can't, we have to make sure that we recognize that when we're tuning the
Can you
gains.
just add, if you go to the first window, that one, I think you can add a compensator right there where C is in the system data for this guy.
Yeah, so that's what this is.
Well, if you go back to the architecture thing,
Yeah.
and then go to system data, and so then right there you can change C to whatever you assigned it in your code,
Yeah.
and that works too.
Okay, so you could do it that way too. I mean, it's a pretty cool little tool. I like it. I'm just, I mostly like it for the intuition it can give you for if you move the 0 around, what it does. So that's a tool. It's available on MATLAB. I recommend playing with it. And yeah, so any questions, I guess, on the how to do PD compensation or PD control? We're going to do it again in a minute because we're going to do PID next. And so, what?
I was gonna say, how come MATLAB doesn't have like a ramp function like it has a step function?
That's a good question. Does it not have a ramp function?
Or you can put in a 1/s in the series with the transfer function and just use step,
Yeah.
and that works too.
Yeah, that would work too. I don't know if it might have a toolbox that has ramp. I feel like I've seen ramp before, and it might just be tucked in a toolbox. Yeah, I don't have the toolbox if there is a toolbox. I mean, one thing is if in MATLAB maybe you'd barely need it because if you're using a ramp function and you're handing it like time, all it is multiplying it by 1, right? So like you don't really need it a lot of times to do ramp. You just hand it the time vector. But. Okay, guys, that's a unit ramp, and you can scale it by just multiplying it by a factor. So ramp's pretty easy. Okay, I think that's it for this lecture then. Is there no other questions?